welcome back to our machine design series, where today we are talking about joints. Once again, this is part 3 of our 3-part mini series. Today's our season finale. We're going to talk about external loads applied to bolted joints. So we're going to take what we learned in the first 2 parts of this series, where we developed a model for the stiffness of the fastener and the stiffness of the members using linear springs to relate force to displacement for those two. In those 2 parts, we defined the fastener as having a stiffness of KB, and the members have a stiffness of KM. Okay, so looking at a diagram of our bolted joint, let's bring this up. What we've done is we've taken this bolted joint and we've replaced it with a model of that bolted joint with 2 springs. So one spring represents the members and one spring represents the fastener. So our fastener spring has a stiffness of KB, and then we have a member spring with a stiffness of KM. Now, let's recap what happens when we apply a preload. So when we apply a preload to this bolted joint, we tighten the nut on the bolt. So this nut is going to cause the threads on this bolt to be pulled down, causing an elongation of the fastener. So this fastener is going to elongate. At the same time, as we're tightening the nut, we are pressing down on the clamped members. So our bolt is being elongated and our members are being compressed when we apply a preload. So we can work out the amount of elongation and compression using Hooke's law, remembering that we've idealized these as being springs, so we're elongating the bolt spring and we're compressing the member spring. So the fastener gets elongated by delta B, which is equal to Fi, our preload, divided by KB, which is our bolt stiffness, just Hooke's law. And at the same time, our members get compressed by the preload divided by Km. And this is just a magnitude, right? One of these will be negative, one will be positive, depending on your sign convention. But remember that the bolt is being elongated and the members are being compressed. Okay, and also the members are almost always going to be stiffer than the bolt. So if we think about a standard bolted joint, these 2 clamped members here that we've drawn, let's imagine that they're made out of steel. So when we're compressing on this solid steel, it's not going to compress all that much. But now the bolt, which maybe it's also made out of steel, but it's a smaller section of steel, right, that's being elongated. And so we're going to get more elongation out of the bolt. And mathematically, we can write this as Km is greater than KB, almost always. And therefore, the magnitude of delta M, the magnitude that we're compressing the members, is almost always going to be less than the amount that we elongate the bolt. That all just has to do with the preload. Okay, so now let's talk about what happens when we apply an external load. Okay, let's apply external load P. And this external load is tensile in nature, so we're going to be pulling apart the members and we're going to be pulling apart the bolt. So we're applying tension to both the bolt and the members. remember that the members had some compression load on them from the preload, and so now we're applying this external load. We're going to be pulling them back apart, so relieving some of this compression. Now, when this external load is applied, some portion of it goes to the members and some portion goes to the bolt. So it gets shared between the two components. So our total load P gets split between PB and PM, the portion that goes to the bolt and the portion that goes to the members. Now, when we apply this external load, we're also elongating the bolt and the members. And when we're doing that with the external load, we are going to elongate them by the same amount. So when we were applying the preload, we elongated the bolt by a larger amount than we compressed the members. And that's because the way we're applying preload is that we are turning the nut on the bolt. But now we're applying an external load, so we're pulling apart the members, and the amount that those members get pulled apart is going to be the same amount that they pull apart the bolt. So mathematically, let's write that out. So with the external load, we elongate the bolt by an additional delta B, and the members elongate by the same amount, so that delta B is equal to delta M. And we can apply Hooke's law once again to say that delta B is equal to the portion of the external load that goes to the bolt divided by the stiffness of the bolt. And we've already established that that's also equal to delta M, which is then equal, using Hooke's law, to PM over Km. Okay, so all we're doing in this step is applying Hooke's law for the bolt and for the members, and then rearranging this slightly, we can find that the portion of the external load that goes to the members is equal to the stiffness of the members divided by the stiffness of the bolt times the portion of the external load that goes to the bolt. Now, our ultimate goal is to get all of this in terms of things that we know, things that we can calculate. So what can we calculate? We can find the stiffness of the members and the stiffness of the bolt. We can do that using methods we established in our first two videos on this mini series of bolted joints. And we know the external load, usually, or we can figure it out. So I don't know how much of the external load goes to the members and how much goes to the bolt just yet, but I do know that the total external load is equal to the sum of PB plus PM, right? So I can rearrange this to say that PM is equal to the total external load minus the portion that goes to the bolt, and I can substitute this into our previous equation to find an equation for the portion of the external load that goes to the bolt. And it turns out that the portion of external load that goes to the bolt is equal to the stiffness of the bolt times the external load divided by the stiffness of the bolt plus the stiffness of the members. And we also will write that as CP, where C is a very important constant in the analysis of bolted joints. It is equal to KB over KB plus KM, and it is called the stiffness constant of the joint. Okay, so I highlighted a bunch of stuff there because this is very important. This is the key to understanding the power of bolted joints. So before we discuss that any further, let's just write a couple more equations so that we can look at this in more detail. We can also write an equation for the portion of the external load that goes to the members. It is just equal to P minus PB, or 1 minus C times the external load. And that tells us that the resulting bolt load is going to be equal to the sum of the portion of the external load that goes to the bolt plus the preload. So the total resultant bolt load is here. And remember that we add these two together because the external load is tensile, at least in this example. So that is positive, and when we apply a preload, we also cause tension to develop in the bolt. So those two loads get added together. And of course, the portion of the external load that goes to the bolt, we just established that that is equal to C times P, where C is the stiffness constant of the joint and P is the total external load. Then we can write something similar for the resultant member load. Now remember that for the members, the portion of the external load that goes to the members is tensile, so that's positive, but the preload causes a compression of the members, and so we have to subtract that off. And also we established that the portion of the external load that goes to the members is just equal to 1 minus the stiffness constant of the joint times the total external load, and then subtract off the preload to get your total resultant member load. Now, this resultant member load is very important because if it ever becomes positive, then these equations will no longer apply. Okay, so these only work when our resulting member load is negative. In other words, this means that the clamped members have still not separated when the resultant member load is negative. They're still in contact. If the members ever separate and are no longer in contact with one another, then all of the external load will go to the bolt because the bolt is the only thing that's holding everything together. If I come back up here, just try to draw that really quickly. If we ever get to a situation where now these members are separated by a distance. Okay, here we go. So if we ever end up in a scenario like this one, where the members have actually separated, then all of the external load has to go through the bolt. So all of this work that we've done only works when our members are still in contact. And that is why it is so important to ensure that your preload is high enough to keep those members clamped together even when your external loads are applied. So, with all of that said, let's draw a joint diagram that helps us visualize these loads that are being split between the bolt and the member when external loads are applied. Okay, so for a joint diagram, we're going to draw the magnitude of the load on the y-axis, and we're going to draw the elongation on the x-axis. So an elongation positive is going to be on the right, and then compression will be on the left. So first, let's just talk about what happens when we apply our preload. So when we apply our preload on the bolt is going to elongate, and this slope of this line, can you guess what it is using Hooke's law? It's KB. So this is the stiffness of the bolt that we worked out in our first video on bolted joint analysis. And when we reach our preload, we have an elongation of the bolts equal to delta B. That's the elongation we were talking about in the beginning of the video. That's Fi. Now, at the same time, our member is also going to reach that same magnitude of preload. It's compressive for the members. And the slope of this line, now you should really be able to guess what this is. It's Km. So that's the stiffness of the members that we worked out in our second video on bolted joints. And when we reach our preload Fi, we will have compressed the members by delta M. Okay, so our preload is a load-controlled type of problem. We're applying the same amount of load to the bolts and to the members. They experience a different amount of elongation. But now, when we apply an external load, we have a displacement-controlled problem. Both the bolt and the member are going to displace by the same amount, and the external load P gets split between the two of them. So first, let's think about the bolt. We're applying an external load P, and it's going to increase the load that is felt by the bolt by PB. And we will end up at a load on the bolt of FB. So that's the preload Fi plus PB. Now, on the members, we're going to, well, first let me label here. We've got an additional elongation of the bolt that is delta B. Now that delta B is the same amount that the members also get elongated. So we started with a compressive load of delta M. We are now stretching the members, so we're going to move towards the positive delta by delta M, which is the same as delta B. Okay, and the amount that we change the load on the members is PM. That's the portion of the external load that goes to the members. The total external load is PB plus PM. Okay, so FM is equal to Fi, our initial preload, minus PM. That's another equation that we wrote earlier. So this chart just shows us the relationships between all of these different parameters, the loads and the elongation or compression of the different members. It shows us the relationship between all of these using our model of the bolted joint as a pair of springs. Okay, so this also helps us see the real power or the strength of bolted joints. So let's say that our stiffness constant C is 0.20. So if C is equal to 0.20, then the bolt takes what percent of the external load? It only takes 20% of P. And the members take 80%. You can see that in this chart, right? PB looks smaller than PM, and that's typical. So a stiffness constant of 0.20 is pretty typical for a standard bolted joint. And that means that when we apply an external load, only 20% of it actually goes to the bolt, and the other 80% goes to separating the members. This is very important, particularly when fatigue loading is present. So when we have fatigue loading, our amplitude, which originally was equal to P, is now equal to 20% of P for the bolt. And so this shows you the real strength and versatility of bolted joints as long as we ensure that our preload is high enough so that the members stay clamped together even when we're applying external loads. So even when the member has to take 80% of the external load, it needs to still remain clamped together. We still need to have some portion of that initial preload that is still clamping them together. As long as we do that, then only 20% of the external load will go to elongating the bolt any further. So this is very powerful mechanic of bolted joints. It is what allows them to be so versatile. It's why they're so widely used, or at least part of why. All right, so I hope this helps you in your bolted joint analysis. Let me know whatever you're working on. I'm interested to hear about it in the comments below, and I hope this was helpful. Thank you for watching. In the next one, we will talk about bolt strength, so the tensile strength of bolted joints. We'll talk about what proof strength means, and then we will talk about the torque-tension relationship, which will let us ensure that adequate preload is developed in a bolted joint. We know that's important, so we'll talk about that in a future video. Thank you for watching, and I hope to see you in the next one.